Example number 1. Horizontal circles, like on a surface, like a car turning a corner or a merry-go-round. Okay, we're going to just take a look at that one. So this is viewed from above, something going around on a surface. And remember, the direction of the net force must be towards the center of the circle. So we're going to look at this point here, and the net force has to be towards the center of the circle. So we call that FC. Okay, we won't put that in our free body diagram. Here's the car headed towards us. So here it is. A free body diagram from the point of view that the car is driving towards you. What is the force pushing you to the center of the circle this time? Okay, so this is towards the center of the circle. So we could label this as FC, but that would be wrong because you never put the net force into a free body diagram. What is the force there? Well, first of all, it's on the ground. So we know this is the normal, and we know this is the force of gravity. And guess what? If you're on ice, you don't turn. And if you're not on ice, you have enough friction, therefore you turn. This is the frictional force. It is the frictional force that pushes you into the center of the circle. Okay? Now, that's all the forces there are. This is the direction of the net force. This is the direction of the net force. And we just have to add up every force in that direction and subtract every force against it. And that has to equal MA. Okay, so what do? We write down the sum of the forces is equal to F net equals MA. Now, in this chapter, I'm going to be very tempted not to put F net anymore, but call it FC, because it's a centripetal force. And if you don't put MA, but you put mv squared over r, that's fine too. mv squared over r. Because that's Newton's second law for circular motion. There's only one force acting on it. It's the force of friction. So the force of friction, which is equal to mu mg, because it's on level ground. There's no weird normal happening here because the normal has to balance the force of gravity. Those have to balance. So mu mg is the force of friction, is the only force acting. That has to equal mv squared over r. Now, normally if this was multiple choice or anything like that, I would encourage you to cancel out the m's. But this time, I'm going to keep the m's in there just so we actually get the values of this force. So mu is what we're trying to find out. What is the coefficient of friction necessary? So 0, this is mu. The mass is 1,500 kilograms. And G is 9.8 newtons per kilogram. We're just going to assume we're on the Earth. Is equal to 1,500 kilograms times V. So V, you're going at 10 meters per second. And it's not just V, it's V squared all over 50 meters. In case I didn't read the question out loud to you, let's just do it right now. A car drives around a 50-meter looped road, okay, radius loop road at 10 meters per second. What is the coefficient of friction necessary to stop the 1,500-kilogram car from slipping? Okay, or it could be even just an orange truck in a parking lot. So 1,500 times 10 squared divided by 50 is we need a frictional force of 3,000 newtons. So then mu is going to equal 3,000 newtons divided by 1,500 times 9.8. So divide this by 1,500 and also divide it by 9.8. And we get a coefficient of friction of 0.204. If the coefficient of friction was any less than this, the car would not make this corner, would slide off the road. If he drove any faster, he would slide off the road. If he tried to cut the corner a little sharper, instead of doing 50 meters, bring it down to 49, he would lose out and the car would slide out of the circle. Okay? Next one. Any questions? Example number 2. Hanging objects like a tether ball going around a pole, or a toy plane hanging from a string from the ceiling, or like rides like the Atmosfear. Here's the Atmosfear at Playland, at the P&E. Okay, and what we have here is a line, the poor sucker up here, and we have the angle, and it's going around in a circle. Now, we're looking at it from the edge, so we can't see it, but it's going behind and then coming out front, and it's doing the old circle there. Okay? So what we do is we draw our free body diagram from the point of where it's at in this picture there that I've labeled. We have a tension force here, a tension force there, and a force of gravity here. That's it. And when we add up those two forces, it has to be a force that's this direction, because that's towards the center of the circle. So what we do is we draw this tension plus the force of gravity, and that has to equal that, which is going to be FC. That's the net force. So it becomes a nice right angle triangle in here in Physics 12, and we just use SOHCAHTOA and Pythagoras and solve it. So here's a question that does it. 0.15 kilogram toy is being suspended as shown from the ceiling, and it's flying in a circle at a constant speed. What is the period of motion of this airplane? Okay, so T is the period, is what it's asking for. Okay, so what we want is to solve this triangle that we have drawn here. This is our force of gravity, and this is our angle here, 33 degrees. And this is our force of gravity, which is going to be mg. So mass is 0.15 kg, and g is 9.8 newtons per kilogram. So the force of gravity, this side of the triangle, is going to be 1.47. So let's hold on. 0.15 times 9.8. 1.47 newtons. So in a triangle, let's just redraw it without all the confusion in this. This is 1.47 and this angle is 33. And we want to get this opposite, this FC. So FC is going to equal, because the tan of 33 is going to equal FC over 1.47, opposite over adjacent. So FC is going to equal 1.47 times the tan of 33. So we multiply this by the tan of 33, and we get that the centripetal force, FC, is equal to 0.9 5, 4, 6, if you want, take a lot of sig figs in there, newtons. Now that doesn't answer the question, but that gets us really close to it. FC is the net force. And that's equal to MAC. Now we have two formulas for the centripetal acceleration. That's either V squared over R or 4 pi squared R, whoops, I have the square on the wrong one, pi squared R over T squared. Since we're asked for the period, it makes sense to use this one, because that has the period in it. Else we'd got the velocity and then have to do one more step. So let's plug it all in. 0.9546 is equal to the mass 0.15 kg times that centripetal acceleration, which is going to be 4 pi squared R, which is 0.55. That's the first time that number's coming into our formula here, into our works, the radius of that circle, all over T squared. So T squared is going to equal, pull out our calculator, I will just quickly go through it. It'll be 0.15 times 4 times pi squared times 0.55, and then I have to divide it by that centripetal force. .412, and now I have to square root it. I will get the period is equal to 1.847, and the units for that will be seconds. Multiple choice, C. Any questions? Here we go. Example number 3. Amusement park ride like the Roundup or the Gravitron. These rides spin fast, which causes a feeling that the patrons are pushed against the wall. And sometimes the walls fall out and the people are stuck to the outside wall. Okay, let's just take a look-sees at a video here. Faster and faster. They feel that they're being pushed against the wall harder, and then at a certain point, the floor falls out and goes down. You don't want to hear the scream. So, this person is here on the wall. Let's take a look at it. What's happening to that person on the wall? There's our free body diagram of the person on the wall. Okay, so what's weird is the normal force is this way. The surface pushes that way. There's still gravity pulling down. So what stops them from going down, since the net force is in this direction? The force of friction. The force of friction is them sticking to the wall. This is why they will not let you use cooking oil all over your clothing before you go into this ride, because you'll slide down on that wall and die. Or at least have fun as you hit the bottom of the ride. Okay? So, and remember, just going to erase this, but again, force of friction and normal will be at right angles. That's a right angle always there. So, a rider, 50 kilogram, rides this Roundup ride, and it has a radius of 5 meters. If the normal force is 30% more than her weight, how many seconds does it take to go around once? Okay. So we have that the normal force is 30% more than her weight. So the normal force is 130% the force of gravity. And her force of gravity is 1.3 times mg, and that's going to be 1.3 times mass 50 times g 9.8, and 1.3 times 50 times 9.8, 637. Now, the sum of the forces is going to equal the centripetal force, which is going to equal MAC. There's only one force in this question that's pushing towards the center, and that's the normal force, and we have its value. So that's going to be 637 newtons, and that has to equal the mass, which is 50, times AC. So AC is going to equal, divided by 50, 12.74 meters per second squared, which is not a bad ride. In fact, this will be kind of fun because it doesn't make you weigh very much more than you regularly do. Just a little like 1.2%, 120% G, 20% more. So, but it's asking for is how many seconds does it take to go around? So it's asking for the period. So we'll use 4 pi squared r over t squared. So this gives us t squared is equal to 4 pi squared r, which is 5 meters, divided by this acceleration of 12.74. So this will give us a t value of, so this is going to be the square root of 4 times pi squared times 5 divided by that value. So it only takes about 4 seconds for that person to go around, and that person will be safe and not slide down that wall. We could also determine what force of friction they need, but we won't. But if you took a look at that video that I showed, they have like a leather or very sticky material there, so you don't slide down. Let's do the example number 4, which is the vertical circles. Vertical circles come in 2 different flavors, either too fast or too slow. And where they meet, it's just the right speed. Okay? In all cases, there are 2 points of interest in a vertical circle, the top and the bottom. So the first one we're going to do is a Ferris wheel. A Ferris wheel is a slow ride. You're going too slow to throw everyone off the ride. Okay, you only need seatbelts in there in case you do something stupid. Okay, because you're going around in a circle. So you never are upside down, hopefully, in a Ferris wheel. Okay? The ride moves around on the slower side, and gravity is always acting down, and the chair you sit on is always pushing up, and that's the normal. However, the center of the circle is in a different location from top to bottom, and that makes a difference. So let's draw the free body diagram. At the bottom, we have the force of gravity down and the normal up. The totally different free body diagram at the top, we have the force of gravity down and the normal up. How is it different? Because different ones are winning. At the bottom of the ride, the top of the circle is straight up. At the top of the ride, the circle is down. So when we do winner minus loser, at the bottom of the ride, it's normal minus force of gravity is equal to MAC. The top of the ride, its force of gravity minus the normal is equal to MAC. It makes a difference. The free body diagrams are the same, but Newton's second law looks at it just slightly different because a different one has to be winning. So let's look at this example here. A 35 kilogram child rides a Ferris wheel of radius 12 meters. The child moves in a vertical circle at a constant speed and completes one rotation every 9 seconds. As the child travels over the top, what is the magnitude of the force that the seat exerts on the child? Okay, first of all, the ride stops. Let's just do that one, just as a separate thing. As he stops at the top of the ride, how much force is being pushed up on him? His force of gravity. Let's calculate his force of gravity. mg. Let's just get this. 35 times 9.8. And that's going to be 343, I think. 35 times 9.8. Okay, so that's his weight. And at the top of the ride, let's draw the free body diagram, even though I have it right above there. The normal and the force of gravity, and the force of gravity has to be winning because that points towards the center of the circle. So we're going to write down the sum of the forces is equal to F net, which equals MAC if we want. So we get the winning force of gravity minus the normal is equal to M. Now, which version of AC will I use? It has the time in it. So to me, it just makes sense just to write down 4 pi squared R over T squared. Its force of gravity is 343 minus the normal. I'll put that in a different color because that's what we're asked to calculate. Is equal to the mass of the child, 35 kilograms, times 4 pi squared. The radius is 12 all over 9 seconds squared. So let's calculate what this centripetal acceleration is and centripetal net force, centripetal force. So 35 times 4 and then pi squared times a radius of 12 divided by 9 squared. That's going to equal 204.7 newtons. So 343 minus N is equal to that. So N is just going to equal 343 minus that number above, which is 138.3 newtons. 2, 1. Example number 5. In a fast roller coaster or a loop-de-loop in a jet, the person moves on the faster side, not too slow, but too fast. Gravity is always acting down on them. This time, the chair that you sit in must push you towards the center. So that means you're upside down. So at the bottom of the ride, you look like at the bottom of the Ferris wheel, it still has a force of gravity down and a normal force up. Just like the other two we just finished. But this time the top of the ride is significantly different because both the force of gravity needs to pull you down and a normal force down. So we get normal minus the force of gravity is equal to ma. That's Newton's second law, the sum of the force, the winning minus losing. And here we get force of gravity plus the normal is equal to ma. So let's try this question out on a roller coaster. A roller coaster carrying a 75 kilogram man has a speed of 11 meters per second at the top of the circular loop. What is the normal force acting on the man at the top of the loop? Okay. So let's again just calculate the man's weight, mg, and his mass is 75 kilograms times 9.8. 75 times 9.8 will equal 735. Now, we do the sum of the forces is equal to Fc, which is equal to m v squared over r. We're choosing the other one this time because it's not a time one. It doesn't have time in it, so we'll use velocity. And the free body diagram is both the force of gravity and the normal force pushing down. So it's force of gravity plus the normal is equal to m, which is 75, v, which is 11 meters per second squared, over the radius, which is 12 meters. So the force of gravity is 735 plus the normal is equal to, let's calculate what the centripetal force is. The net force is mv squared over r. So 75 times 11 squared, let's try to do that. Okay, delete. 11 squared divided by 12. 756.25. So the normal is going to be very little. .25 newtons. And we'll talk about roller coaster design in a moment. It's very circular, very physics-like, not very applied physics. Okay, here we go. Example number 6 is a fun one to take a look at it. This is the special case between 4 and 5. It is special because it is the point where you just start lifting off your seat. It is the point that if it's a roller coaster, the change starts coming out of your pocket upside down. Or your car is just about to lift off the ground, or it starts lifting off the ground. You're going over the hump in the road just too fast so the car lifts off the ground. At that point, the normal force becomes 0. You're just starting to lift off. So the only force acting on you is the force of gravity. And that is it. So the sum of the forces is equal to Fc is equal to mv squared over r. Okay? And the Fc is the force of gravity. So the force of gravity, mg, is equal to mv squared over r. Not r squared, r. Okay? There is a question here. How fast must the Ferris wheel turn in example 4 to make the rider feel at the top weightless? Okay, and that was the 35 kilogram boy. I will have the results for you in a moment. Continuing on, here we go. This is number 3. It was a 35 kilogram child on a Ferris wheel. Boom, boom, boom. And we now want the rider to feel weightless at the top. That means what makes you feel weightless is that not the force of gravity is 0, but the opposing force is gone. There usually is a normal force up there, and that's what you feel pushing on you. And when that disappears, that makes you feel weightless. So, boom, got to get rid of the normal force from the other time. We calculated the boy's weight to be 343. So we want his weight, 343, to equal mv squared over r. So 343 has to equal his mass, which was 35 kilograms. V squared over the radius is 12 meters. So now we just solve for that, V, and we get 343 times 12 divided by 35. That'll be V squared, and then we have to square root it. And we get 10.84. So we just have to increase the speed up to 10.84 meters per second. What was it before? Well, beforehand, let's do it in red here, his velocity was, the circumference, 2 pi r over t. And that's the case. 2 pi r is the distance around the circumference divided by the time, distance divided by the time. And when we plug those numbers in, let's just do it. Instead of writing it down, 2 pi r is 12, and divide it by the time, 9. His speed beforehand was 8.37, 8.38 meters per second. So change his speed from 8.38 to 10.84. He is now lifting off the seat at the top. It's like, woo! He's going around and he's almost lifting off the seat. At that point, he's not touching the floor. At least he's not feeling the seat push up on him anymore. That normal force is now 0. And any faster, he's going to be lifting off. Cool stuff. Okay, example number 7. This is an interesting one. Here we go. The corners of a road are often banked to assist the cornering of cars. Cars are aided by the banked corner to help turn that corner. And here is a picture I found of one of those indoor bicycle racetracks, and look how steep that corner is, just so that they can go around the corners, and all they have to do is worrying about pedaling and getting fast instead of worrying about friction and them sliding off the track. Imagine a bobsled corner without banking. They would slide right off. So let's look at that again. This is a skeleton ride here. This is a person going down head first. But look at the banking on that corner. Just to be able to do it without friction. Yeah, it's crazy banking. So this is a corner that we're doing without friction. So the car is coming around the corner, heading towards us here, and it's on a banked corner, and let's call it black ice. There's no friction on that, so that he still continues the corner without sliding off the road. So there's only a normal force and a force of gravity, and those two need to be adding up together so that it becomes a centripetal force. So I'll draw our free body diagram. Again, it's just, whoops, that's not even, let's say normal and a force of gravity down. That's it. And they need to make a triangle, so you end up with a normal and the force of gravity, and you end up with the centripetal force. Kind of like the tetherball one. Now they're asking, a curve has a radius of 50 meters and a banking angle of 15 degrees. That will be 15 degrees. And that will be the angle between the normal force and the force of gravity as well. Will also be 15 degrees. So this is 15 degrees. What is the ideal or critical speed for this corner? Okay. So we have that we'll use these things, 15 force of gravity and centripetal force, that the tan of 15 is equal to the centripetal force all over the force of gravity, which is going to be mv squared over r all over mg. Now, we're not given the mass of the cars. Luckily, it does cancel out. We don't need it. That's why there's no cars, no roads that say you have to be this weight else you slide off. It doesn't determine them. The mass doesn't really matter. So we get v squared over gr. Okay? We have the radius is 50 meters, so we can solve for v. So tan of 15 is equal to v squared over 9.8 over 50. Pull that out on a calculator. 9.8 times 50 times tan of 15. That'll be v squared. And then square root it. The speed is 11.46 meters per second, or if you want in kilometers per hour, it's around 41 kilometers an hour. That's how you do banked corners. Again, it is drawing out the triangle and relating that the normal and the force of gravity is the centripetal force. This is what you usually want to work with, and you usually are given the force of gravity. We could calculate the normal force, but we don't need to. Thank you for paying attention to this long video. Subscribe, click on the likes, enjoy.